This is Sugar. What do you think, Sugar? Can be a star? Be an internet star? Alright, sorry to be so heavy on Dennis Pagen, but he writes most of our hang gliding stuff. I know there's some more modern stuff. There's podcasts and stuff, but I'm here to get us caught up with all my ground school articles that I have for my students on my forum. Read them in case someone wants to listen to them while they're driving or something like that. This is Thermal Lore Part 7 by Dennis Pagen, 2004. I recently had a chance to experience nature as most people experience it, while sitting in the glow of my television set. I was watching a short film depicting the spectacular Yosemite Gorge with time-lapse photography. It was morning and fog was strewn in ragged layers across the canyon. The early thermals were lifting off near the walls as the deep valley heated. You could see the effect of successive thermals pulling the fog back and forth as they released. The fog was stirred, drawn up, and generally moved like a floating sheet of ice on a swirling stream. The film was an amazingly clear picture of how thermals affect the flow of the ground wind, at least in a confining valley. Once a group of pilots and I were soaring at a local site in winds of 10 to 15 miles per hour. We were sustained by the ridge lift, but when a thermal passed through, we latched onto it, and to our surprise, we drifted forward as we climbed in it. This happened time after time. When the flight was over, we discussed the experience and concluded that some of the thermal mass was originated from the sheltered backside of the mountain and had upwind momentum by the time it cleared the ridgetop and entered the general wind flow. Isolated waterspouts have been seen when the sky is cloudless. Dust devils have suddenly appeared which have ripped the traditional target of tornadoes, house trailers, apart. The pyramids of Giza serve as thermal triggers and often have cumulus clouds above them. Thermals in very hot spots can rise more than 3,000 feet per minute. That's 35 miles per hour. In thunderstorms, bump that up to 70 miles per hour or more. The lift in a strong thermal can carry us upward in a rush, only disappear in an instant and surround us with sudden sink. Thermals can appear on a cold overcast day and far out at sea. They can fail to appear at times on a day with strong bright sunshine. They can be everywhere you turn, or as elusive as a gambler's gaze. All these items and more point to the complexity and many facets of thermals. Anyone who flies in thermals for a time experiences this complexity and must understand as much of it as possible in order to be successful and excel. While each thermal is somewhat unique, and some are downright quirky, they all obey the law of physics and demonstrate some aspects of behavior we can take to the bank. This month we will focus on a variety of thermal qualities that help round out our store of lore. Thermal tops. Here we will investigate what happens at the top of a thermal's vertical passage. The dead zone. Most thermal pilots have had many experiences of climbing in a healthy thermal on a good day with cumulus clouds studding the sky, but never being able to climb close to cloud base. When this happens repeatedly, we sometimes begin to wonder if we sprang from the shallow end of the gene pool. But don't question your ancestry yet, for there is good reason for this dead zone below the clouds. In fact, it is so well known that it has a name, the subcloud layer. It doesn't say to go to that. Seems like a good time to go to that figure one. Most of us are aware that a similar volume of air is sinking earthward and must replace all the thermal production pushing upward during a day. We also know that the sinking air is more widespread than the thermals, which are generally cohesive blobs moving with greater vertical velocity. But the distribution of sink is not typically uniform. It tends to be strongest near the thermal or cloud margins. In fact, when the cloud forms, the sink near the thermal edge becomes stronger. To understand this last point, cast your memory back to 8th grade science class when you're staring out the window, dreaming of flight, and miss the concept of latent heat of vaporization, LHV. Now you have a reason to pay attention. When moisture evaporates, it does so because some of the water molecules have more energy than others. In effect, they get knocked out of the fluid by combining hits from other dancing water molecules. This result is the molecule has enough energy to remain in a gaseous state, and the liquid it came from is cooler by a tiny amount. This process occurs millions of times, and a certain amount of water vapor becomes suspended in the air. The suspended water molecules acquire the same temperature as the surrounding air molecules, but they have much more energy, that being the energy required to escape the attraction of other water molecules in the gas, which is the LHV. When water vapor, a gas, rises with a thermal, it condenses back into liquid water droplets at the dew point as the rising thermal expands and cools. The dew point is essentially where cloud base is located. The changing of water from a gas to a liquid releases the LHV, which in turn heats the surrounding air, and an acceleration of the lift occurs. The LHV of water is the greatest of any liquid, and in fact is the highest of most materials, except some metals that boil at thousands of degrees centigrade. So if you can imagine the great rush of lift at the level of cloud formation, the usual result is a circulation of air around the thermal being forced down and inward beneath the thermal, as shown in Figure 1. This down-moving air is stable because it is heated by compression as it sinks, and so it forms the subcloud layer as shown. Already showed that one. So Figure 1 again. The subcloud layer typically extends 200 to 600 feet below the general cloud-based level. According to Wallington in Meteorology for Glider Pilots, 1977, the subcloud layer normally exists on high-pressure days. Wallington was considered to be the world's authority on soaring weather when I met him at the Hang Gliding World Meets in Australia in 1988. He has since expired. I would add that the subcloud layer is most common with dry layers around the vicinity of cloud base for reasons we will see below. How can you use this information? The obvious answer is to quickly recognize the situation and to not waste time trying to get higher than a certain level when going XC. On the other hand, if you are playing King of the Mountain, in order to get head and shoulders above the rest of the floundering flock, apply extra patience and tighten up those circles to use the best central cores when you hit the lid imposed by the subcloud layer. The formation of the subcloud layer is similar to the widespread suppression of thermals by the general sinking air in a high-pressure system, or in the wide area surrounding thermal clouds, including thunderstorms. In such situations, it is easier for thermals to rise in the paths of previous thermal tracks. This effect is especially prominent when there is enough wind present to drift the clouds over new sources of lift. The trick is to recognize the high-pressure system and suppression of lift and expect thermals to be limited to previous paths. Without clouds, of course, this technique can be difficult. Cloud suck. Another common effect we blunder into often enough is cloud suck. This effect is almost the opposite of the dead zone, although the origin is the same. Cloud suck occurs when a cloud has grown large enough that the downward moving air around the edges does not disrupt the thermal cores from rising under the cloud. Look at Figure 2 and you will see how the vacuuming cloud, accelerated by the release of LHV as before, takes in air from below, which continually feeds the heat exchange process. This process, overgrown, is what creates a thunderstorm. When a cloud reaches a certain size, air rushing in from the side can no longer satisfy its voracious appetite, and cloud suck occurs. A moist layer at the cloud formation level helps induce cloud suck because the cloud doesn't quickly evaporate, which would cool the surrounding air. I expect that cloud suck occurs when relative low pressure systems or moist conditions abound or convergence is happening. I have encountered the most severe cloud suck in the American western deserts and other areas where heat lows develop. Detecting and escaping cloud suck. I have often been asked in my travels how to detect cloud suck. Besides the conditions given above, I use ongoing observations. When clouds grow to a certain size, horizontal dimensions, not vertical, I start taking precautions. I was once entertained by the clouds suck in the Owens Valley under a very spread out cloud with no impressive vertical dimensions. It was entertaining because I eventually escaped, after perhaps an illegal episode of terror, and enjoyed a rush of pure adrenaline. I put that experience into the databank and have used it to fly more safely. Other matters I look for in terms of cloud formation are rapidly growing clouds and dark bases. Dark cloud bases occur when the lift at cloud base is strong and the condensation is occurring rapidly. Needless to say, cloud suck does not occur when there are no clouds. The next thing I pay attention to is the flying effects. If a thermal I'm climbing in begins to smooth out or does not slow up when I reach a level of 500 feet or so below the cloud, lower the larger the cloud and the stronger the lift. I widen my circles to see if the lift is widespread. If so, I begin to expect cloud suck and gradually swing my circles to the one side of the cloud. This side is determined by the cross-country direction I am heading or the safest escape route, that free of clouds. If the lift increases at any point, I know that the suck is for real and I will fly fast out of the lifting zone. With practice, a pilot can learn to time it right so the desired height is achieved just as the cloud is cleared. It is inspiring to watch racing competition pilots do this. Pilots of lesser experience should leave much more margin in sucking conditions. It is one of the most terrifying things in flying to be sucked into a cloud unwittingly and unwillingly. Okay, at this point I'm going to cut in and not wait till the end. So most of the time our margin is 500 feet below a cloud, so he's talking about illegal flying here. And if they're competition pilots, if someone's going for a record, actually, the flight is supposed to be legal for it to be a record. And so you should be exiting under the cloud at 500 feet under the cloud. And another thing I want to point out, he's talking about drifting the circle to the side or the front of the cloud, whichever is the safest escape route. That's good, but keep in mind that if you have to level out to escape the cloud, that your sink rate is better. So if you're climbing pretty good and under a cloud and you're turning, expect a much faster climb as you level out to escape the cloud. So once again, I don't like his margins and his bragging about the comp pilots popping out right at the edge of the cloud. So you should be popping out with 500 feet of clearance as you're clearing the cloud. And a lot of times you can climb up the side of a cloud, amazingly enough. So I'll go to figure 3. No, we're not there yet. The more aware you are in the air, the less likely you are to be caught in cloud suck. But if your awareness has been dulled by too much aviation ecstasy, here are some remedies. Hang gliders should fly as fast as possible to the edge of the cloud. I prefer to have my VG on at least 2/3 for more speed and stability. If the cloud overcomes you, slow down and try to maintain a steady heading with your wings level. See Performance Flying for more details. Paragliders should use big ears, then B-line poles, then other drastic measures to avoid being sucked up. Paragliders normally can't race to the edge of a large cloud. Flying in a cloud can have severe consequences, as pointed out in our various manuals. One final thing to point out is the occurrence of both cloud suck and suppression of thermals. Sometimes it happens that the thermals are rising through a general area of sinking air, so most of the thermals never get near cloud base. At the same time, the clouds look good and are lingering due to auto-feeding from the air just below and beside the cloud. This effect is the explanation for those exasperating days when the clouds look great and the lift is stingy. Thermal bottoms. Here we look at factors in the lower part of a thermal's stature. Thermal shapes. Thermals come in a variety of shapes. We know this from our experience with more than 100 gliders all in one thermal group waiting for the start gate in a competition, and from other observations. I once saw a group of about 100 seagulls thermaling above a garbage dump. They clearly delineated the thermal boundaries and showed its progress as it climbed up to about 1,000 feet. This was a blob, since the lowest birds had to flap a bit as their feathered fellows emitted derisive jeers. We now know that the thermals can be a single column, individual spheres, multi-chord groupings of lift, strung out patches along lift lines, and, some speculate, even rings. I've been the victim and the evictee in a situation where being just 50 feet below a pilot climbing in a thermal made the difference between climbing or floundering. I recall one flight in Brazil where several of us desperately needed lift. I arrived at a circling group just below them, and despite a frantic but systematic search, found nothing. They pulled up the ladder. Sometimes the lower pilot has not gone to the right position, but there are times when I have been climbing and the pilot right below me can find nothing. These frustrating situations occur for two reasons. First, the thermal is a discrete ball or blob. It is probably rising like a vortex ring or donut, turning itself inside out. See Figure 3. Its vertical dimensions is not much wider than its diameter. Lucky are you to blunder into such a patch of lift while others go home empty-handed. Secondly, the thermal can be such a narrow core that half a wingspan displacement will result in a miss. This possibility has been demonstrated to me many times. Recently, in a meet in Florida, I was an exuberant core climbing at 700 feet per minute. I came up from below several pilots. They all moved over, but couldn't find the core as I sailed on by. That thermal lasted for about 4,000 feet of climb, so I know it was of extensive vertical development. They should have been able to find it, but it's sometimes hard to nail a core when it is tight in wind. Of course, too, I have been the hapless pilot unable to find a pencil core. Figure again. As we mentioned in last month's installment, learning the nature of the day's thermals can at least give you an idea of how to search. Note, for search techniques in calm or in winds of various types, see our new book, Secret of Champions. Thermal sources. We have written extensively on thermal sources and only wish to point out some highlights here. You perhaps have heard that such things as towns and rocks are good thermal sources. In my experience, these areas are only good later in the day. Rocks have a particularly high heat capacity, which means quite a bit of heating must take place before the surface temperature changes significantly. I once spent part of a sunny day repeatedly visiting a rock outcropping to feel its temperature. It remained surprisingly cool until mid-afternoon. However, it was giving off heat well after the sun went down. In my experience, towns are the same. They have a lot of surface to heat because of their vertical structure, so they store up considerable heat. Note that the air temperature in a sizable town is typically 10 degrees warmer than the surroundings. But the buildings tend to block the wind, so thermals are not initiated as readily. Just like rock outcroppings, I don't expect to get thermals over a town until after 2 to 3 p.m. Trees are a more extreme example of this delayed reaction. Because of their vertical dimension, they can store a lot of heat to be released later in the day. Pine trees are best for this action because they don't transpire as much as deciduous trees. Water is the material hungriest for heat. It will absorb all day with its top layer warming a bit, but not nearly as much as ground in the same conditions. Then, when the sun gets low and the ground cools at night, water can release heat for hours. Most of us now know to expect thermals to be lurking most readily over high ground of an area. Let's take a moment to figure out why. Generally, there are at least 4 reasons. First, the slopes on a hill, ridge, or mountain facing the sun will heat much more than flat ground where the sun strikes a glancing blow. This factor is especially true in cooler months when the sun is lower in the sky. Secondly, any upslope wind, anabatic flow, helps drag warm air towards the slope and helps initiate a thermal's rise. A general wind flowing into the slope will do the same. Thirdly, the downwind side of the hill can block the wind and allow a larger thermal buildup. Finally, the higher the ground, the cooler the surrounding air, so the greater the difference between the heated air over the surface and the nearby air it must rise through. Even a very slight rise in the terrain works in these manners. For example, the famous Florida Ridge is where it's at if you're racing on this former beach state. This ridge is only a ridge to a Lilliputian. It is barely higher than the rest of the state. The downside of having ridges above, say, 500 feet in height, to tell you where to look, is that they organize the thermals so much that the lift is suppressed nearly everywhere else. In my area of Pennsylvania, the long ridges are great thermal sources, but don't expect to find any thermals in the 5-mile wide valleys unless your luck is unusual. In areas lacking much vertical definition, other things can be relied upon to spot thermalists. Back in Florida, in the recent meets, cloud base was relatively low and the clouds were not reliable. They would often dissipate as soon as you reached them. But many of us commented on how we would locate thermals at the cloud shadow edges. The theory is that the cold area in the shadow next to the warm areas as in the sun causes a little circulation that disturbs the heated air at the ground and gives it impetus to rise. The warm air gathers vertical momentum, a thermal is born, and then gliders are born. I expect this process takes place only when winds are light, so that the shadows aren't moving too fast. What you can use. In the first part of this article, we discussed the near cloud experience. We already provided some practical guidelines in those sections. We'll only repeat here that making the decision when to leave a thermal as you get within spitting distance of a cloud depends on your experience, your goals, your glider type, and what you have previously encountered during the flying day. If you are merely trying to get high, by all means struggle in the diminishing lift below a cloud, unless it is obviously deteriorating. Experiment with different bank angles until you can stay in the shrinking cores. On the other hand, if you're trying to make time and distance, wasting seconds in scrabbly lift is not the game plan unless you're low. If clouds are showing a dead layer beneath them, chances are all the clouds will be the same unless one grows outsized. The converse usually isn't true. If a cloud is sucking, it doesn't mean that the others will. Size matters. Another pattern to be watchful for is the thermal forms. If you find several thermals to be columns, chances are most of the rest of them will be on that day. Of course, be ready for the rogue thermal that has its own idea about a proper thermal shape. Versatility in making decisions on the fly are what distinguish a good pilot from mediocre boater. Finally, we wish to point out that the desirability of recognizing alternate thermal sources when your first choices, usable clouds in my book, don't work. Know your ground cover. You can learn a lot about thermal sources in your area without even flying. Spend a moment in the Walmart parking lot and note how hot the tarmac is on various days with different cloud cover. Also note the effects at different times of the day. Do this for grass, bare ground, crops, or whatever you find locally. Then relate this data to what you experience in the air. Eventually your store of knowledge will be usable in real situations where you need a saving thermal, or you want to linger aloft as the sun slowly sinks. All right. Thanks, Dennis.